In this video, we will be discussing more volume of solids of revolution. In particular, we're going to discuss the cylindrical shell method. Just as a way to motivate the method, let's think about taking this region bounded above by y equals 2x squared minus x cubed, and bounded below by the x-axis. So this region right here, and rotating it around the y-axis. Now in the last section we learned about the disk and washer method. So this is what we would have done with the disk or washer method. Remember, first thing we do is we sketch the region. And the axis, which happens to be the y-axis. And then we sketch a reflection of that region about that axis. So I'm going to do the best I can. Here's my region. And if I reflect it, it's going to look like that on the other side, roughly. It's kind of like looks like a bundt cake to me. If I factor out an x squared here, I have 2 minus x over here. This function equals 0 when x equals 0 and when x equals 2, so it crosses at 0 and 2. So you get this sort of bundt cake looking thing. All right. Now in the last section, if I wanted to use the disk or washer method to find the solid that I've generated here, this bundt cake looking shape, I would slice this region, or slice my solid perpendicular to the axis. And remember, our axis is the y-axis. That's how we got this reflection. So I'm going to slice perpendicular to that axis. We see a little gap, so that's a washer rather than a disk. Alternatively, you can slice the original region into representative rectangles and think about taking that rectangle and rotating it all the way around. So in the reflection, you'd see that rectangle over here. And then you say to yourself, okay, what's the volume of these slices? So we sliced perpendicular to the axis. I know I just said it, but I just want to give you that checklist of things to do. And now you want to find, well, you have to decide between disks and washers. And delta x versus delta y. And then you want to find the formula for v sub I. So that's our method, remember. So when I sliced perpendicular to the axis, I could see, just from looking at my slice, that I had a washer. Now, if you're not as good with geometry, if you try to slice it and you're like, I still can't visualize what's going on, one thing that really helps a lot of students is to say, okay, if I draw that slice perpendicular to the axis, that representative rectangle, if there is a gap between that axis and the rectangle, or a gap between this whole region and the axis, like that big old gap right here, that big old gap, if there's a gap, that means I'm dealing with a washer. Okay, and then the width of that slice, or the thickness of that slice, is that tiny vertical distance delta y. Time to throw that marker out. Or alternatively, we can look at that width of the representative rectangle, that's delta y. So I've got a washer, it has a width of delta y. All right, and now I just have to find the volume of that washer. Well, we know volume of a washer, volume is something that looks like this. It's area times the thickness. Area of a washer is area of the small or large circle minus area of the small circle. Factor out your pi. Now the question becomes, well, what's the large radius and what's the small radius? I just need r sub I here and little r sub I there. So I need little r sub I here and big R sub I there. All right. So how do I find those guys? Well, let's look at big R. It's horizontal, so it's going to be x on the right minus x on the left. X on the left is easy, that's just 0. But x on the right, well, that's another thing that's easy. You just take this equation and you solve for x in terms of y. Generally that's easy, but it's not easy this time. I don't just have an x cubed here, I've got a 2x squared minus x cubed. Now there is, we have the quadratic formula, or quadratic equation, excuse me. No, quadratic formula, I was right the first time. Gosh, I'm getting tired. We have the quadratic formula, which allows you to solve for x. Similarly, there's a cubic formula. We could solve for x in terms of y using the cubic formula, but nobody knows the cubic formula, and we can look it up online, but it might take us a while. And then we have to somehow differentiate the x value on this side from the x value on this side using that cubic formula. So we're not actually going to do this. Since it's very difficult to solve for x in terms of y in this equation, we're going to do something else. Instead of revolving the region around the y-axis and then slicing perpendicular to the axis, instead of slicing perpendicular, this time we're going to slice parallel, and we're going to form what are called cylindrical shells. So don't do this. We're going to try another method because it's difficult to solve for x in terms of y on this function. All right. So we're here. It looks like this, roughly. Got my bundt cake function, bundt cake volume. Okay. So we still start exactly the same way. This is called the cylindrical shell method. You'll see why in just a second. So you've sketched a region and your axis. You sketch the reflection of the region about the axis. And then once you've done that, instead of slicing perpendicular to that axis like we did with the disc and washer method, we're going to slice parallel to the axis. And this is the key. You're taking this and slicing this way instead. So our axis was vertical, now our representative rectangles are also vertical. Now I'm going to imagine taking this one little rectangle, which has a width of delta x, and rotating it around. So when I take this and rotate it around, I'm going to see it over here as well. It should have the same height. If it was a better picture, it would. And then and try to add that third dimension to it. What we're going to get is like a cylindrical shell. If I take a rectangle and I rotate it around, I'm going to get something that looks like this. Or even better, let's not draw it on those axes. I'm going to get something that looks like this. Now the way I tend to think of it is I think of like a koozie. Whenever we do this in class, I break the koozies out and we try to come up with the formula for the volume of this thing. It's like a koozie without a bottom or without a top. It's just a shell like this. Or you can think of like a can of beans. You got your can of green beans from the grocery store. I'm not talking about the volume of the beans inside. I'm talking about the volume of the metal all around the outside. That's what we're talking about. Not the top, not the bottom, just the metal on the outside. Question becomes, how do you find the volume of something that looks like this? And how does that give you the volume of this? Well, before we get to the equation for that, remember, you're doing this over and over again. So this rectangle that's adjacent to that one is a little shorter. I'm taking that rectangle and I'm revolving it around 2. And that's giving me a shell. And then there's a larger one out beyond that. I'm taking that rectangle and that's giving me a shell. And I don't know if you see it, but it's like we've got all these shells nested inside each other. Over here, we're going to see some taller ones with some shorter ones around them, and even shorter ones, but they're wider. Inside here, we've got like shorter ones, and then taller ones, and then taller ones, but they're nested. It's like Russian nesting dolls. So if I can find the volume of one of these, and I'm imagining all these shells that are nested inside each other, that little ones here, and then I'm going to have a largest one in the middle, and then there are going to be ones around that, and ones around that, and ones around that, until I get the whole thing. Well, if I add up the volumes of all those shells, that's going to give me the volume of my bundt cake. Okay? So I just need to find the volume of one of those shells. Well, the way I think of it is I'm taking this thing, it's just like a can of beans, it has a seam on the side. If I want the volume of that outer piece, like this outer edge of my can of beans, I just cut it down the seam and I'll unfold it. I'll lay it out flat like this. So I get that. Alright. Now that's just a rectangular slab. I can find the volume of that pretty easily. It's just length times width times height. You just have to find the length, width, and height in terms of properties of this shell or properties of this curve over here. Okay, so let's think about it. The height of the shell is the height of that rectangular slab, so that hasn't changed. And that thickness of this shell, that distance from there to there, that delta x, that came from the thickness of that rectangle. So I took that rectangle and I rotated it around. It has a width of delta x. So that shell has a width of delta x. So that's delta x. And then this distance that's a distance all the way around a circle. That's circumference, right? This is circumference of that circle. And the circumference of a circle is 2 pi times the radius. Now you might be saying to yourself, well, there's an inner radius and an outer radius. We're going to have to do that same thing that we did on the last set of problems. And the answer is no. Because in the limit, that delta x is going to become infinitely small. And when that delta x becomes infinitely small, that outer radius and that inner radius, they're going to become indistinguishable. So the volume of this piece is just 2 pi times the radius of the shell times the height of the shell times delta x. So we found the volume as circumference, I'm going to abbreviate that, sub I times height times thickness. So that's 2 pi r times h sub I times thickness, which in this case is delta x. And if I can find this and this in terms of x, I can find the volume as an integral in terms of x. And then I can evaluate that integral and it will give me the volume of the whole thing. Now I stopped writing my steps out, so I'm going to go back to writing my steps. We sketched the region and the axis that we're revolving around. We sketched the reflection of that region about the axis. So this guy appears over here in the reflection. And then we slice parallel to the axis and then rotate that rectangular slice around the axis, or revolve, I keep saying rotate, revolve the rectangular slice about the axis and draw a representative cylindrical shell. Then, once I've got my shell, I cut it down one side, I unfold it, and I get this. And so the volume of that shell is the circumference times the height times delta x, and I get my volume formula. You're going to choose delta x or delta y, and then you're going to find the radius and height of the shell in terms of the appropriate variable. Then you're going to state v sub I, and you're going to use v sub I to come up with the integral. Okay, so we're going to do this one again, but without all those nested shells on it, just to make it a little bit cleaner and easier to see what's going on. Okay. So it looks roughly like this. I like my little bundt cake picture. I think it's pretty. Oh, not my picture, but that one's really bad. Okay, anyway. So you sketch the region, sketch the reflection. Slice parallel to the axis. And you end up with something like this. Take that slice and rotate it around. I'm sorry, this is such a bad picture, guys. And then try to sketch a representative shell. Now you look at your representative rectangle and you're going to decide whether it's delta x or delta y. Well, you're going to choose between those two, and you're always going to choose the one that is given by the width of your representative rectangle. Not the length, but the width, that smaller dimension. Since our smaller dimension, the width, is in the horizontal direction, that's delta x. So we choose delta x. And now we need the height and the radius as functions of x. Well, on the other problems, we had maybe one radius or possibly two, but the radii were always in the same direction. You're always doing top minus bottom, or the top y value minus the bottom y value, or x on the left versus x on the right, or x on the right minus x on the left. But you were never doing both in the same problem. With cylindrical shells, you're always doing both. One goes in one direction, so there's my height, and one goes in the other direction. There's my radius. Now, if it's vertical, you're still doing the top y value minus the bottom y value. But you need the top y value minus the bottom y value in terms of x. And here, you're still doing x on the right minus x on the left. Then you need those x values in terms of x as well. I know it's a little weird, but you need y minus y in terms of x, and x minus x also in terms of x. So let's write those down for this particular problem. I need the top y value minus the bottom y value. Well, y was given by this equation. It was 2x squared minus x cubed from earlier. We're talking about the ith subinterval, so we're going to pick an x value there. We'll call it x sub I. The bottom y value, that's on the x-axis. So that's y equals 0 down here. So it turns out to just be the function this time. It's not always the function. It's always that distance there. Okay, so we've got our height as a function of x, and we want the radius. Now this stumps some people. They usually can go along, but they're like, okay, Miss Townsend, I'm not 100% sure I agree with you or I understand it. Okay. X on the right versus x on the left. X on the left, that's the y-axis. That's clearly x equals 0. So this is 0. We're good there. Now x on the right, I'm just going to call x. You're like, what? It's just x? How do you know it's just x? Well, here's the idea. Let's say I was at the point x equals 3, y equals 2. And somebody asked me for the distance from the y-axis out to that point, that horizontal distance. Isn't it just 3? Isn't that just the x value over here? And how about this vertical distance? Isn't that just the y value too? So if I'm at a point xy, the distance from here to here is x, and the distance from there to there is y. And you might say, well, how is that? That's gonna mess everything up. How are we going to take care of the height of that function? How are we going to get, I mean, if I'm just plugging in an x, how's that going to work? Well, this height is going to go with that x. So when I'm 1 unit out this way, the height is going to be 2 minus 1. It's going to be 2, or 1. Or if I go like 1.5 units out this way, the height is going to be 2 times 1.5 minus 1.5 cubed. And it's going to give me the right height. So this is taking care of the function. The height is taking care of the function. This x value is just saying start at x equals 0 and then keep going and keep going and keep going until you get to x equals 2 and stop. And meanwhile, you're multiplying that by the right height, the height that goes with that particular x value. So it all works out. X on the right this time is just x. And so we've got x minus 0 there, and that's our radius. Okay. So now we got to state the volume. Now my cylindrical shells go up and down. They're like this time. I'm doing a really bad job of my drawings today. It's okay. But then I unfold it and I lay it out flat and it looks like this. This dimension here is the width of that rectangle, so it's delta x. So that becomes delta x over here. The height here becomes the height here, or I'll use capital H to be consistent. And then this distance is the distance all the way around, which is the circumference, 2 pi times the radius. So volume is 2 pi times the radius times the height times delta x. And we just found the radius and we just found the height. We said the radius was x sub I. And the height was 2x sub I squared minus x sub I cubed. Now in some books you're going to see 2 pi x times f of x. Do not memorize that. Memorize this, because things are going to change if we rotate it around some axis other than the y-axis or the x-axis. I need you to understand the geometry. I need you to be able to find the radius in general and the height in general, and then show me when I'm asking you about those questions. I'm asking you to solve these problems on a quiz or a test. Okay, so that's our volume of one piece, total volume. It's approximately the sum as I goes from 1 to n of those volumes. We've got n little shells. I want the volume of each shell. Add them up. Total volume is the limit as the number of shells goes to infinity of this guy. And that guy is an integral. That is the integral of 2 pi times x times 2x squared minus x cubed. Integrate with respect to x. And we integrate from one x value to another. Careful here, it's not negative 2 to 2. We sliced this original region into rectangles, and we rotated those rectangles around. The rectangles that show up on this side are only reflections of this side. So we really only need to add here. We need to add for the x values from in the original region, not in the reflected region, but here. So x starts at 0, ends at 2. We're integrating from 0 to 2. Now if you factor out the 2 pi, you're going to have to distribute your x in order to get to a point where you can evaluate the integral. X times 2x squared is 2x cubed. X times negative x to the third is x to the fourth, negative x to the fourth. Bring your 2 pi down. Bring the 2 down. Add 1 to the exponent, divide by the new exponent. Here, add 1 to the exponent, divide by the new exponent. Plug in 0 and 2 and subtract. So I've got 2 pi times, this is going to simplify to 1/2 times 2 to the 4th minus 1/5 times 2 to the 5th. And when I substitute in 0, I get 0 minus 0, so it's just 0. So I've got 2 pi, 16, half of 16 is 8, and then I've got 32 over 5 there. So 8 is 40 divided by 5. So 40 minus 32 is 8. So I get 8 over 5 times 2 pi, 16 pi over 5. Units cubed. That's the volume of my bundt cake. Okay, in the other videos, we will look at problems where we're integrating with respect to y instead of integrating with respect to x. We'll also look at problems where we are revolving our region around an axis other than the y-axis or the x-axis, so that you can get a sense of how that radius changes in those cases. But remember, if it's horizontal, it's always x on the right minus x on the left. If it's vertical, it's going to be the top y minus the bottom y. Be careful here. With cylindrical shells, you're going to have x on the right and x on the left, and y on the top and y on the bottom every time. But the width of that rectangle is going to tell you whether all of that needs to be in terms of y or whether all of that needs to be in terms of x. It's very careful that you differentiate between those two cases, that you know the difference. So we're going to do more examples in another video.